Bike Lift Kit Project for ME223, presented by Team Purple, Darren Mabe, Mark Garber, Calvin Connor, and Vince Schwartz. This is our video presentation promoting the kit we have designed for professors to give to their students as a tool for learning. We have designed a kit that will give students everything they need to build a bike lift prototype. Our kit is intended for college-age students who have a basic understanding of mechanics, electronics, and programming. They will also have to have basic computer knowledge to aid them in programming the Arduino. As a student, it is hard to find usable materials for lab within your budget. You may have some good ideas, but don't know where to get the necessary materials. Our kit solves this problem by giving you some basic materials and ideas, but doesn't limit your creativity, simply gets you on the right track. Professors will enjoy the fact that our kit is simple and easy to use and understand. They will also appreciate that our kit still forces the students to think for themselves, but also doesn't leave them not knowing what to do. Our kit keeps in mind the core human drives. Most importantly were the drives to learn and to experience. Our kit gives the students some basic materials but forces them to be creative and think for themselves. Our kit also targets the desire to bond and acquire by helping to make the project more enjoyable and requires students to work together to come up with the absolute best product.
The code for the Arduino is reasonably straightforward. When the Arduino is powered on, it reads the voltage over the potentiometer as a variable, and then uses that variable in a function that sets the power output to the DC motor. This process is repeated, and the power variable updated, until the Arduino is powered off, with a 100 millisecond delay between each loop. The bike lift prototype uses a system of gears and pulleys to create a high mechanical advantage. The DC motor is attached to a spindle that turns a friction gear. The gears provide a mechanical advantage of 14. This larger gear is attached to another spindle, which is also attached to a smaller gear. And this system also creates a mechanical advantage of 14. And finally, the line attached to the bike is wrapped around a small spool on the second spindle. This pulls the line through a double pulley system, which creates a mechanical advantage of 2 and lifts the bike.
The physics fundamentals that are necessary to understand this project are that force is equal to mass times acceleration. We have a mass and we want to accelerate it away from Earth against its gravity. So we have to decide what force to apply to it. The second is that power is equal to the change in work over the change in time. We have a set amount of power and want to do the most amount of work in a reasonable amount of time. One of the major ideas introduced in the bike lift project is that of mechanical advantage. Pulleys create mechanical advantage by splitting weight. A single simple pulley simply redirects a force, but a pulley with one end attached to a rigid member essentially has two forces going up in a free body diagram, letting the rigid member do half the work for you. Every time you add another pulley with this same idea, you cut it in half again and again. With gears, they increase force by reducing speed and increasing torque. The smaller your drive gear and the larger your driven gear, the more torque you create and the lower the RPMs that are outputted. The electric motor is a key part of our kit. To understand how it creates force, you must understand how it works. Electric motor is essentially two sets of magnets. One is a permanent set of magnets on the outside, and the other is an armature, which is an electromagnet, and a commutator with brushes attached to the axle. As the electromagnet is turned on, there is a force created between it and the permanent magnets. This causes the axle to spin. As it spins, the brushes attached to the axle and the commutator cause the magnetic field to switch as it passes a certain point. This causes the new magnetic field to cause the axle to rotate again. One of the key goals of the bike lift project is to get the motor to run at an efficient level. Motor efficiency is measured as the drop in power input, which is measured in current times voltage, and the power output, which is designated by the change in work over time. A motor is always most efficient at a certain RPM. This is decided by the ratio between torque, power, and RPMs. The highest amount of torque is always created at the lowest amount of RPMs. Where power has a curve, it has a peak in the middle of the RPM range. And efficiency is similar to the power curve, but generally slightly lower, involving more torque.
Mechanical advantage is multiplicative, so the total mechanical advantage of the lift system is 392. The maximum load that is able to lift is approximately 80 grams, and this was mainly limited by the friction gear and the low current and voltage that the Arduino can provide. Using a 30-gram mass, we achieved an efficiency of around 42% for the entire system.
During the project, we applied life skills. For example, critical thinking. As we problem solved, each idea was introduced with critical thinking. When designing or improving our prototype, every idea followed the process of critical thinking. First, some problem, like gear design, or some other problem we were facing, was defined. Then a solution was presented, followed by a technical or a logical reason for the solution. And lastly, as a team, we evaluated the idea and its reasoning. We applied critical thinking to amplify our results and to get those results faster. Also, we applied reflective thinking continuously after each interaction with group members. Our communication improved drastically because of reflective thinking. In the beginning, we did not share ideas very efficiently. We spent most of our time trying to explain our ideas rather than critical thinking. But after reflective thinking, we started drawing diagrams of our ideas and showing through example with physical objects, oftentimes with our prototype, to gain understanding throughout the group faster, so our sessions were much more productive. As we developed our prototype and learning kit, we kept a pad of paper to illustrate ideas to improve communication as well as keep track of our developing ideas. At the end of each session together, we recorded our final conclusions so we could start right off from where we left during the next meeting. We had one pad for the project, full of our collaborated notes and ideas so any person in our group could reference the collective knowledge and ideas at any time. We also applied the life skill teamwork. We had a common goal of wanting to get a high grade in this project, so we started to work by the mantra, hard work and good engineering yields good grades. At the beginning of each meeting, we set goals on what amount of progress we wanted to achieve before departing. At the end of each meeting, we established what each person must accomplish before the next meeting, and each person always had those assignments done.